Neural networks have evolved from simple pattern recognizers into powerful architectural engines of logic that form the backbone of modern global infrastructure. They are no longer just static tools for pattern matching. Today, they function as autonomous systems capable of executing complex tasks across the globe. We are now in the era of adaptive learning. Networks can update their internal weights in real time as they ingest new data without forgetting what they have already learned. From energy grids to life saving precision medicine, neural networks now power the core infrastructure of our society, continuously optimizing our world. Traditionally, neural networks process data sequentially, like reading a book word by word. This made it hard to understand long range context. Transformers changed this. By using attention mechanisms, they analyze the entire dataset at once, deciding which elements are most important to focus on simultaneously. Imagine an attention head that highlights key connections. Instead of treating every word equally, it learns to prioritize relationships between relevant parts of the input. This allows the model to map complex dependencies across long sequences, making modern AI vastly more accurate and capable than its predecessors. Deep inside every neural network, data flows through individual neurons. Each connection carries a weight, functioning like a volume knob that dictates how much influence a piece of data has. A high weight means the connection is strong and signals will pass through with more impact. A low weight dampens the signal, making it less influential in the final decision. Biases act as activation thresholds. Even if input signals are strong, the neuron will only fire if the accumulated input crosses this specific threshold, allowing the network to filter out irrelevant noise. To improve, neural networks must learn from their mistakes. This process is called backpropagation. When a network predicts incorrectly, we calculate the error between the actual output and the desired result. Using backpropagation, the error is sent backward through the layers. This image illustrates how the network identifies which connections contributed to the error. A feedback wave moves backward, adjusting the internal weights, like turning knobs, to minimize this loss. Repeated thousands of times, this feedback loop drastically reduces the error, allowing the network to master complex tasks. Neural networks are evolving beyond text. Multimodality allows a single network to process text, audio, video, and sensory data simultaneously, merging these into a universal conceptual space. We are entering the era of agentic AI. These systems don't just answer questions, they plan and execute multi-step tasks autonomously by interacting with the environment. AI agents can now interpret visual interfaces and control browser applications to perform research, manage software, or execute digital workflows on our behalf. By combining multimodal understanding with agentic planning, AI systems are becoming versatile digital agents, capable of handling complex challenges that require logical reasoning across diverse environments. The frontier of neural networks moves beyond software to specialized hardware. Neuromorphic chips physically mimic the brain's spiking neurons to achieve massive energy savings. We are entering the era of green AI. Techniques like pruning and quantization are making models up to 90% more efficient, requiring far less electricity for inference. However, as these networks grow in complexity, they become opaque black boxes. Researchers are now racing to develop explainable AI, or XAI, to provide human-readable reasoning traces. The future lies in bridging the gap between raw computational power and transparent, energy-efficient intelligence. We are building systems that act with agency, learn with intent, and explain with clarity.